So this is how it works. Suppose you have a gas collection tube in a beaker. Okay, and what you've done is you've filled this completely with water. Okay, and then what we do is you can have a reaction, and this is the setup that you'll be using. Other diagrams you'll have, like what we did with zinc in 110. If you took this in 110, you'll have basically a generator. Okay, so suppose I have magnesium and hydrochloric acid. And what happens is it forms hydrogen gas and magnesium chloride. When it does form a hydrogen gas, this goes through and it bubbles up in here, in your tube. Okay? So when you bubble up the hydrogen gas in your tube, it begins to displace the water. When you look at your water, remember you have a concave meniscus, and when you read it, you're going to read at the bottom, okay, of your meniscus. Okay? So when we collect gases over water, this is called by water displacement. Okay. So what happens here is this. When we look at this volume here, this has hydrogen gas. I agree with that because basically this is what we're doing. It's a gas generator, right? But the other thing is that after you displace it, there's more than just hydrogen gas in here. Because remember, I'm collecting over water. So you also have water vapor as well. Okay? So if you've ever looked at the difference between being next to a lake on a hot, hot summer day versus being in the middle of Death Valley, you find that being next to a lake is a bit cooler than being in Death Valley. And the reason is you have water vapor. So some of that heat that gets absorbed converts your water to the gas phase. So how much water vapor that you form is going to be temperature dependent. So we don't have a pure gas in here. What we have is we have water vapor and hydrogen gas. So let's say pressure inside the tube. Okay, so I'm just going to say pressure inside. Now that's going to be equal to the partial pressure of hydrogen and the partial pressure of water. All right? What else do we know? So when we read here in your tube, it goes from 0 down to 50. So suppose we had 36.5 milliliters. If we read this at the bottom of the meniscus. So the volume of gas that we collected, this is the gas mixture. This is hydrogen and water vapor. Let's say is equal to 36.5 milliliters. But we need to know something else. We need to know what the pressure outside is. Why do we need to know that? Because we're looking for the hydrogen pressure, because that's our product. That's what we formed. This one, you can look up. But how do we find this one in order to finish our equation? So you need the outside pressure, and that's from your barometer. Okay? So suppose we read our outside pressure, and it's something like 765.8 millimeters mercury. Okay, and you would basically read your barometer, just like we talked about in experiment 13. Okay, you would basically look at the top and you would correct it. Okay, so basically, if you corrected it, you would look at your mercury vapor pressure in the table in your lab packet. Okay, so suppose this is already corrected. Okay, if it's not, then what you're going to do is you're going to look at the room temperature on the barometer. Okay, and then you're going to do the correction table. Okay, so you do that. Okay, so suppose that your room temperature, we said last time it was 18.1 degrees Celsius. And so the correction table says at 18, and this is close to 760. So this is 2.2 millimeters mercury. Because mercury actually doesn't have zero vapor pressure, but you can see here it's extremely low. So we want to correct for that. Okay, so now that we know this, what do we do with all this information? Okay, so if I have my corrected outside pressure, then how does that relate to my inside pressure? Okay, so let's just go through and take a look at this diagram. Okay, what do you think about my outside pressure? If my outside pressure is less than my inside pressure, then what you would expect to see is that if my pressure outside here is less than the pressure here, then you would expect this to push down below and push as much liquid possible to the outside. This would be below the level of water that's in my beaker. Okay? If my pressure outside is the same as my pressure inside, then you would think that the lines should be equal. And in fact, in a sense, if you've ever taken the Chemistry R110 lab and did the Charles law, one of the things that we had to do was we moved our flask until the levels were equal, so we knew that the pressure outside was equal to the pressure inside. But in this case, when we're collecting gases, the pressure inside, if you see that this is higher, that means my pressure outside is strong enough, it's pushing more liquid up here. So how do we know what that pressure inside is? That pressure inside, this is P inside, plus this height in millimeters mercury is equal to the pressure outside. And this is going to be in millimeters mercury. Okay, so let's stop for a moment. Let me erase the board, and then we'll go from there in terms of what to do with all this information. Okay, so we have a volume of 36.5 milliliters. Pressure outside 765.8 millimeters mercury. Correction was 18.1 degrees Celsius, 2.2 millimeters mercury. Okay, so let's find out and get everything together. Now, what is the goal? We're talking about partial pressures, and we're using it to calculate something, okay, when we collect gases over water or any other solution. The process is the same. So in this experiment that we're doing right now, the goal was to find the mass of magnesium. Okay, so let's talk about what we have and what we still need. We have pressure outside, 765.8 millimeters mercury. And if we're going to do the pressure corrected, okay, that's going to be 765.8 plus the pressure of the mercury. Oh, can add here. 10, 1, 8. Okay. The volume of our gas is equal to 36.5 milliliters. The other thing, we will just redraw the setup here. Is that when we find what we need to do is that height, we need the height to find out what P inside is versus P outside. This height you measure with a ruler. Okay, so suppose this height was, oh, let's just say it's 14.7 centimeters. Okay, now this is, by the way, we're using water, because aren't we collecting our gas H2 over water? So we need to convert this height from 14.7 centimeters, okay, water. We need to convert it to millimeters mercury. Okay, so we know that this is the same as saying 147 millimeters water, because we know that there are 10 millimeters in 1 centimeter. What's more interesting is to convert between the millimeters water and the millimeters mercury. Basically, it's 13.6 millimeters water for every 1 millimeter mercury. Now, how did I get this number? This number, 13.6, is the density of mercury. So it's almost like the density of mercury and the density of water. But here, 1 millimeter of mercury, because it's much denser. So I don't need as much to have the same mass, the same weight as water. So I needed this much water to have the same weight as mercury. So when we do that, we find this is equal to 10.8 millimeters mercury. Do we have everything in place yet? Not yet. There's one other thing. And the other thing is this. We need the temperature of my gas. So you can see that in this collection of gases over water, there's a lot of moving parts. So I'll summarize all the moving parts again for you at the end. Okay? And then we'll go on to our next subject. Okay. So if you measure the temperature in there, suppose the temperature of the gas itself is going to be about, say, 18.8 degrees Celsius. So this one needs to be converted to Kelvin. But from this temperature, we can get the pressure of the water vapor. And the reason we can do this is, remember, water vapor, water is a pure substance. So if we know the temperature, we can actually get our water vapor. Okay, so all you need to do is go to a lookup table. Okay, and when you do go to the lookup table, let me just get my lookup table here. There are many sources. Your lab packet, of course, is one source. You can look it online. That's another source. Your textbook is also an excellent source. If you look at your textbook, the lab packet, the water vapors, that table at the end of experiment 13, where you're looking at the corrections, if you look for that information in your textbook, you will find that in Appendix B, where it says the temperature we said was 18.8, so the closest is 19. In torr, or millimeters of mercury, it's 16.48. Okay, so collecting gases over water, there's a lot of pieces of data you need. So let's go through and see, what are we going to do with all these pieces of data? Okay, so 1, we needed to get the corrected outside pressure. Okay, that's important. 2, from that, with the pressure, the partial pressure of water, we can get the pressure inside the tube. Okay? 3, from, not, can we, let's see, we're at the pressure of water. Hold on. With the height. We can get the pressure inside the tube. And now, with the pressure, the partial pressure of my water vapor, we can get, oh, need a cup of coffee. We can get the partial pressure of hydrogen. Okay? So, and we'll go through this again when we actually do experiment 13 for you to do your calculations. But let me show you your example calculation here. We have a corrected P0. Then with the height we said was 147 millimeters water. We converted that and we got 10.8 millimeters mercury. So we got P inside. And because we know the P inside the tube is equal to the pressure of my hydrogen and water, now that I have the pressure of water, I can get the pressure of hydrogen. So let's go ahead and do that. So, the corrected pressure outside is equal to the pressure inside plus the height. So, all this is going to be in millimeters mercury. So, my pressure inside is equal to PO minus my height. And we said it was 768 millimeters mercury minus 10.8 millimeters mercury. And that's going to be equal to 757, okay, millimeters mercury. Okay, so now we know the pressure inside. All right. Now that we have the pressure inside, let me just go ahead and use some is this piece of data. Okay, so now that we have that, we now have finish 1 and 2. So we have 2 right here. So now let's get the pressure of the hydrogen gas. Okay, so the pressure of the hydrogen gas is going to be the pressure of my inside the tube minus the partial pressure of water. So it's going to be 757 millimeters mercury minus the 16.48 millimeters mercury. Okay, when we do that, what we get is get something like a 741 millimeters mercury. Okay, so now we have the partial pressure of hydrogen. What are we going to do with all this data? Okay, so let's talk about what are we going to do with this data. So, we have gone through, collected gases over water, read our outside pressure, corrected it, looked at the height from the top of the water in the beaker to the top of the water, reading off the meniscus. So we know the height in water, converted that, so I now know what the inside pressure of the tube is. Then from the inside pressure of the tube, I remove my water vapor, so now I know the partial pressure of hydrogen. Now let's go back. What was the original goal? The original goal, remember, was to find out in this reaction the whole goal is to find out how much magnesium we used. So we needed the moles of hydrogen gas, get to moles of magnesium, and get to mass of the magnesium. Okay? So, to get to the moles of hydrogen gas, all of the data that we had used previously was to get to this part. Hydrogen is a gas. So we're going to use PV equals nRT. And we are going to solve for N. This needs to be in atmospheres. That needs to be in liters. This needs to be in Kelvin. So let's do our conversions. The volume, divide by 1,000 to get liters, 1, 2, 3, is equal to 0.0365 liters. Temperature, you're going to add 273.15 to this. You get 291.95. You can say, what about significant figures? We're going to stop here. We're adding, okay, but I'm going to keep it now until at the very end, where our answer should be 3 significant figures. Okay, the pressure, remember, it's 760. Okay, I'm going to move this over so I'm going to go off the screen. The pressure is equal to 741 millimeters mercury. And we know that for every 760 millimeters mercury, that's equivalent to 1 atmosphere. Okay, so we get 0.975 atmospheres. So the first business is to get N. Okay? R, just so you know and have it on the board, is equal to 0.08206 liter atmospheres per mole Kelvin. Okay, so let's go ahead and find out what N is. So N is equal to PV over RT. So I'm just using this equation, dividing both sides by RT. Let's plug in all our numbers. We have 0.975 atmospheres. Let me just erase this so I have some space here. Okay, V, 0.0365 liters. R, 0.08206 liter atmospheres per mole Kelvin. And T is 291.95 Kelvin. Okay, our units cancel out. 1 over moles. So the good part is our units are going to be in moles. So let's find out what we get. 0.975 times 0.0365 divided by 0.08206 and also divided by the 291.95. And we get something like 0.001485 moles of hydrogen. Okay? So far so good. So all of the data that we used, that we collected, the outside pressure, the height, to get the inside pressure, looking at the partial pressure, water vapor, the temperature of the room, and the temperature of your reaction, collection flask, volume of your gas, all that is just to get to this part. Now that we have, we can do the rest. So, since we know the moles of gas, let's just go ahead and finish off the solution. It's 0.001485 gigs moles of hydrogen. And what's my stoichiometry? My stoichiometry is that it's 1 to 1. 1 mole of magnesium for every 1 mole of hydrogen gas formed. It means what I get is 0.001485 moles of magnesium. The molar mass of magnesium is what? 24.31 grams for every 1 mole of magnesium. Okay, so what we get is 0.0361 grams of solid magnesium. So that's a combination, one, of looking at partial pressures and using partial pressures with that law from Dalton. We can now use the partial pressure law in order to get the pressure just of the hydrogen, not of the water. Once we know that, we can actually do stoichiometry problems with this. Okay, so let's stop here, and the next slides, or next lecture, will be on kinetic molecular theory.